In this example, we are going to have a transmission line network which is terminated by a load, and we are going to solve this problem using Smith chart. So we have some parameters like a reflection coefficient, input impedance, standing wave ratios, and we are going to see that how we can use a Smith chart in order to find these values. So let's check our problem. As you see, this is a network. This is a transmission line, like previous discussions, which is terminated by a load, and the characteristic impedance is 50. The length of transmission line is 0.4 lambda, and the ZL is 60 plus 50J. So we are going to find and calculate different kind of things. So I'm going to start with the reflection coefficient at the load. Again, we know that reflection at the load, we calculated this previously. We said that gamma L is equal to ZL minus ZO over ZL plus ZO. So this is how you can calculate the reflection coefficient manually without using a Smith chart, but I'm going to use a Smith chart in order to find this. Actually, we did this in previous section. I just wanted to do once more. So reflection coefficient at the load, first I have to normalize my impedance. We said that ZL is equal to 60 plus 50J. So the normalized impedance is going to be ZL over characteristic impedance, which is 50, then it's going to be 1.2 plus J. And how we can show it on the Smith chart is simple. We are going to show here, so this is going to be my point. I can show with a red dot here. And then I'm going to draw a straight line from center of a Smith chart to my impedance. So this is basically my ZL here. And then I'm going to continue this until I reach a circle which says that it's a angle of reflection coefficient. And if you check this, your angle is going to be 54 degrees here. So this is 54 degrees. And which circle? So I'm going to show it another color, maybe this circle. So let's show it blue. So I'm talking about this circle. So I'm going to show it dashed lines. I'm not going to show the rest, but I'm highlighting just some part of it. So this circle, says that the angle of reflection coefficient. So 54 is going to be angle of reflection coefficient. Let's find the magnitude. So we said that for a magnitude, we have the blue line. We just have to use the blue line in our scale. And it says reflection coefficient E or I here. So this is, if you find this point, it's going to be 0.422. So then reflection coefficient consequently is going to be equal to 0.422, which is our magnitude, with an angle of 54 degrees. So the next question is we want to find the load admittance. So for load admittance, I'm going to again show my impedance here. I'm going to draw a straight line from center to my impedance. So then I will continue my line. This line is straight, and I will continue it to the other part. So with the same length, so this length should be equal. And eventually at the end, I'm going to find my admittance. So then what I have here, this is going to be my ZL, and this is going to be my YL. So if you read this, basically your YL from this point is going to be, let me first write the normalized value. So the normalized value is something close to 0.492 minus, because we are in the lower part of Smith chart, minus J times 0.4110. So here it's not shown precisely. What I suggest you is printing a Smith chart on a paper, and then you can use ruler and pen to do this. So you're going to get exactly this impedance. But on this basically picture, you can see something like close to 0.5. But this is not very precise. I'm just showing you the method. The best way to do this is using the hard copy, and you can just print on a paper, and you're going to get very precise results. So then from here, the YL, our impedance, is going to be the normalized, we have learned this over characteristic impedance, and this is going to be equal to 9.84 milli minus J 8.2 milli, because it's going to be 0.492 over 50. So I'm just writing milli, or you can write 0.009, something like that. So this is going to be my load admittance. So now we are going to talk about the standing wave ratios. This is new. We haven't done this before, but it's again simple. So we want to find the standing wave ratio on the line. Again, we are going to do the same thing. So we are going to draw a line from center to our load. So this point is our load again. So this is our ZL. And this time we are going to use a different scale. So we have the same line with the same lengths, but this time I'm using this part. So this, it says that SWR, as you see here. So then I can just read this simple. My standing wave ratio is going to be equal to 2.46. If you do it on a paper, you're going to see the exact value. So this is the most important part here. We want to find the input impedance, Zin. So let's see how we can find the input impedance. But before going into a Smith chart, I have to talk about something here. So we have two concepts that we have to know here. So as you see, this is my circuit and this is going to be my load. So I have two directions. The first direction is direction toward load. I'm calling it toward load, and it's to the right side. It means that, for example, we are going toward our load. It means that we are going to the right side and we reach our load. But if we go in the opposite direction, it's going to become toward generator. So it's not complicated. You have our load. You can imagine there's a generator or a source here, and this direction is toward your generator. So after knowing these facts, then we can start how we can find the input impedance. I'm going to show the technique. So let's start from the first point. First of all, like we did previously, I'm going to show my load here. So this is going to be my ZL here. So this is ZL at this point. So then I'm going to continue this line. But this time I'm going to use a different circle. So as you see here, it says that wavelengths toward generator. I'm going to check this one, wavelengths toward generator, or it says that wavelengths toward load. It doesn't matter, you can pick one of them. I'm going to pick wavelengths toward generator. Why? Because the reason is I'm going to start from this point. So this is my point A, let's say. Then I will go back like this to the point B. Let's say this is point B. So at point A, I have my ZL. At point B, I have my Zin. And the purpose of this example to find Zin. So it means that I'm going to move from A to B, and I'm going to move toward generator. So we say A to B means toward generator. Sometimes we show it with TWG or TWL. So I have TWG. It means that I'm moving toward generator. So here first I have to read my wavelength. So what is here? If you check, this point is going to be 0.175 lambda approximately. So after knowing this, what should we do? We have to move toward our generator. It means that we are going to have this kind of circle. So we are going to move clockwise on a Smith chart. But the question is that how much we have to rotate. That's the question. The answer is simple, because we say the L is 0.4 lambda. So then I'm going to say that the goal basically is going to be 0.175 lambda plus the length of my transmission line. So I'm going to turn according to the length of my transmission line. So it's going to be plus 0.4 lambda, and this is going to be 0.575 lambda. So then we have to search for this number. Yeah, so I'm going to continue. As you see, this is increasing 0.19, and it goes until it reaches this point. So at this point, I'm going to have 0.5 lambda. So we have not reached this point yet. We have to go a little bit more we have to turn a little bit more. But as you see, after this, there's no, for example, 0.51. It starts decreasing. This is how we show numbers on this on Smith chart, but it doesn't matter. You can just find. So it means that we have like some kind of portion here. We have to go. So this portion, and we can calculate this portion, because as you see, it's decreasing from 0.5. It goes 0.49, 0.48. So what we have to do is just calculate this portion, and this portion is going to be. You can find like the 0.5 minus what is left here. It's 0.075, yeah, 0.075. So this is basically lambda, and eventually you're going to have 0.425 lambda. So you just have to find your point. So then I'm going to turn in a circle because I want to keep the distance. I want to keep the length of this line constant. So I have to move like a circle, and then I will go to the point which says that 0.425 lambda. So which is here, and then after this is simple. So I'm going to draw a line here. So the line should have the same length as the first line. So this is going to be my z. And this point is going to be 0.425 lambda. So you see, I started from 0.175 lambda. Why? Because it shows my ZL. Then I started turning in this direction. So like this. So I turned. I have to rotate like this. And what was the amount of rotation? We said that it's going to be the length of my transmission line. So I have to add this 0.175 plus 0.4, it's 0.575. But we reached to this point, we said that this is the maximum. We don't have 0.575. It ends at 0.5. But after that it starts decreasing. It doesn't matter. We just have to find that portion. What was the portion here? So this portion is basically 0.075 lambda, yeah? So this is what we had left here. Then we just have to subtract it because this is decreasing this time. We just subtract this portion. So 0.5 minus 0.075 to see how much it decreased. And so this portion actually, let me erase this. This portion is basically comes up to here. So from here to this point exactly, I have 0.075. I can also put this there. So this is my 0.075 lambda. So this is my left portion here. I have to decrease it from 0.5, and finally I will reach my point, which is 0.425 lambda. And I'm going to draw a straight line from here to the center of Smith chart, and then I have the length of the same line I had before, and this is going to be my zine. And if you find your zine on a paper, again, I suggest you to use a hard copy. It's going to be approximately 24.5 plus J 20.3. And this is basically the real impedance. You can also, the normalized value is 0.49 plus J 0.406, something. So this is going to be my Z, and this is normalized, and this is basically going to be your real value. So I suggest you to print a Smith chart paper and try it by yourself. You're going to learn it better. So the last thing, we're going to check the distance from load to Vmax and Vmin. So if you check this picture, we said that because we are forming standing waves, we are going to have maximum and minimum amplitude on our line. But we just want to see what is the distance of this, because it depends on distance. Yeah, for some distance we have a minimum, for some locations, let's say, but at some locations we have maximum. So we have to find the first. For example, when we are moving from point A, let's say this is our point A, we are moving toward our generator. We want to see at which distance we are going to have Vmax and at which distance we are going to have Vmin. So this one is similar to other ones. So again, I'm going to draw this. So here I can say Vmax happens here. This is the technique, and minimum happens here. So that's how we find the Vmax and Vmin on a Smith chart. This is the technique. So it means that in order to find my Vmax, I have to move just this portion is going to be basically my wavelengths from here. So then here again I said that it's 0.175, but if you read this number here is, let's say this is lambda, but this number here is going to be 0.25 lambda. So it means that you just have to find the difference. So it's going to be 0.25 lambda minus 0.175 lambda, and this is going to be 0.075 lambda. So it means that let me just erase this part and show it another color. So let me show it the same color actually. So here, if we move little bit toward our generator, at this point we are going to have Vmax, the maximum amplitude, and this length, this small portion here, so this length is going to be 0.075 lambda. So at this point I'm going to have my first Vmax, but then I'm going to have another V. I just have to rotate. Each time you rotate, you're going to reach another Vmax because we don't have one Vmax. We just want to find the first Vmax for now. But there are other Vmax, you just have to rotate on your Smith chart. So let's go on Vmin. That's the same idea. So let me show with the red color. So I'm going to again start from this point and rotate like this. So this is going to be my, basically I'm going to rotate like this, yeah. So then I will reach my Vmin. And what is Vmin? It's 0.5 lambda, yeah, we know this. So again for Vmin, I'm going to find 0.5 minus the first point, 0.175. So these are 2 lambda. And eventually I'm going to have 0.325 lambda at this point. So this is going to be my Vmin. It means that if I move from here to a point, this point is going to be my Vmin. And what is this portion? So this I'm going to show with a red color here. Let's say this is my portion, and this one is going to be, let me show it here. This portion is going to be 0.325 lambda. So that's what we have. But then someone would ask, so what about other Vmax? So for example, let's say here we found this, yeah, number 1, and then we found number 2, and what about this Vmax here? You just have to turn again. If you want to turn, you can just turn like this and go back to another Vmax. So because you can like make so many turns on your Smith chart, yeah. So you can find another Vmax, another Vmin based on your lengths until you reach this value. So this is 0.325. So we already reached our length. So it means that we're not going to have any other Vmax, because after this it's going to exceed the lengths of our transmission line, and we are not going to have any location for having Vmax. So we learned this one too. I'm going to basically delete this and show this Vmin with the red color. I think this is better to understand. So this point is my Vmin. So, and this is basically my start point for Vmin and also both for Vmax. So this was our example, and we calculated many things. We obtained input impedance, extracted the standing wave ratio, input impedance, and distance from load to maximum and minimum voltage amplitude. So as you see, the Smith chart is a very useful tool, and you can use it to find so many things. So in the next section, actually, I'm going to use Advanced Design System software in order to confirm these results. So I'm going to make this network, and I will do some simulations to see our results are correct or not. So next section is going to be simulation, and I'm going to use a Smith chart which is available in ADS.